Hello, I'm Kenji Leibnitz from the National Institute of Information and Communications Technology in Osaka, Japan. The title of my presentation is Evaluating Multiple Access Protocols: Asynchronous Pulse Coding versus Carrier Sense with Collision Avoidance. And this work was jointly done together with my colleagues Ferdinand, Peper and Konstantinos Theofilis, as well as with Mikio Hasegawa from Tokyo University of Science and Naoki Wakamiya from Osaka University. Wireless sensor networks with cheap, small, and energy-efficient nodes will play a major role in the realization of ubiquitous environments and massive IoT applications. These may range from managing home appliances to quality control in industrial facilities. Such communication networks need to follow standardized protocol definitions so that devices can interact with each other, especially when they access a common wireless channel. There are mechanisms for providing simultaneous access, like CDMA. Alternatively, random access methods are commonly used where nodes can transmit at any time. However, they may need to defer the transmission if the channel is currently occupied by another node. In our previous work, we introduced the Asynchronous Pulse Code Multiple Access, or APCMA, as a new multiple access scheme, but we have so far not compared its performance to conventional mechanisms. Here, we compare APCMA with CSMA-CA through simulation and analysis. APCMA is based on the principle of communication through silence. Here, a value x is encoded as the length of the silent time interval between two successive pulses, as shown here by the blue arrows. However, this value becomes impossible to decode if the interval is interspersed by a pulse from another message, indicated by the red arrow. To overcome this problem, APCMA adds redundant pulses such that code words differ as much as possible under all possible shift operations. APCMA is therefore better able to handle collisions because code words are sparse, having only few pulses. And if two pulses from different transmissions overlap, this doesn't disturb the underlying pattern of pulses of both code words. Since only certain interpulse intervals are valid, interfering pulses can be easily identified and rejected. Another important point is that the transmissions don't need to be synchronized, which makes the implementation much simpler. One drawback, however, is that since values are transmitted as unary encodings, the code words in APCMA tend to be longer than with binary encodings. This increases the delay of messages. This is the general format of a code word in APCMA for encoding an integer value x. There are NP pulses shown as blue arrows. The distances between pulses are defined by encoding functions fi of x. Since a code word spans over a constant length of c time slots, the last interval depends on the sum of the first np-2 intervals. This can be used for validation of the code word. Here are two examples of APCMA codes, both of them having 10 code words. On the left is a code with 4 pulses and a code word length of c equals 25, which has a symmetric pattern. On the right is a code with 5 pulses and length c equals 36, where the first 2 and the last 2 pulses have the same intervals as in the left figure. The middle pulse is selected so that any pair of code words has at most 2 pulses in common under all possible shift operations. Let us now briefly describe the CSMA-CA model used in this evaluation. We follow the basic CSMA-CA backoff algorithm from the IEEE 802.15.4 standard. Since the time slot length depends on the frequency band and modulation scheme, we make the simplifying assumption that a unit backoff period matches exactly the length of a single message of 10 bits, and the time for one unit backoff period is 200 microseconds. The superscript C refers to the CSMA-CA model, and the superscript A will later on indicate APCMA. We use the default values for the backoff exponent and maximum number of backoffs as specified in the standard. This flowchart shows how a single node with CSMA-CA is simulated. After transmitting a message, the node enters the sleep state for a uniformly distributed random period. We set the minimum sleep time as 1 time slot. The maximum sleep time is given as a parameter of the simulation. After initializing the backoff variables, an initial random backoff is performed within the interval 0 to 2 to the power of BE minus 1, where BE is the backoff exponent. Then, 2 clear channel assessments are performed in successive time slots, checking for any ongoing transmissions. If both CCAs succeed, the node will transmit the message. If either one of the CCA fails, a new random backoff will be made, with BE increased by 1 and the backoff window size doubled. This process will continue until either the message is successfully transmitted or the maximum number of backoff attempts is reached. After this, the node aborts this transmission and enters the sleep state again. For our evaluation, we count whenever a node has 2 successful CCAs and distinguish the following 2 cases. If node K is the only node beginning to transmit at time t, we increment the value AK1. If there are multiple nodes beside K that are also beginning to transmit at time t, we increment AKM. We track both of these variables for each node, and at the end of the simulation, we calculate the average of their fraction across all nodes to obtain the average success probability for the CSMA-CA simulation. Our simulation runs until a predefined number of messages is generated, and we use the total simulation runtime, T, and message length, L, to compute the CSMA-CA throughput as shown here. When evaluating APCMA, we analytically compute the success probability for APCMA as shown in our previous paper, beside also running simulations. With the average length of sleeping and transmitting phases, as well as the duration of one APCMA time unit delta T of A, we can compute the throughput for APCMA as shown here. This gives us an average pulse density Q, from which we compute the probability p that an arbitrary time slot is occupied by a pulse when there are n nodes. This leads to the Analytical APCMA success probability PS of A, shown at the bottom of this slide. Regarding the APCMA simulations, we compute the success probability as follows. We capture for each node k the number of messages that are transmitted by this node and that are received without ambiguities. We also collect the total number of messages transmitted by node k during the simulation. Averaging over the fraction of these two values across all nodes gives us the success probability for the APCMA simulation. This diagram shows the way we run the evaluation for both methods for the given parameters, number of nodes, n sub n, and maximum sleep time in CSMA-CA S max of C. We use the sleep factor, SF, that depends on the maximum number of time steps a node may be performing backoffs in the worst case. For each parameter setting, we run the CSMA-CA simulation 100 times and determine the success probability for each run. Then, we compute the average success probability and throughput for CSMA-CA from these values. Using the CSMA-CA throughput, we determine the corresponding maximum sleep time for APCMA. From this, we compute the analytical success probability for APCMA. We repeat the APCMA simulation 100 times and take the average of these values. This gives us the average success probability for APCMA. We now show the numerical results for sleep factor 5, which is a heavily loaded system. This figure shows the success probability on the y-axis for the number of nodes in the system shown on the x-axis. The throughput values that we obtained range between 164 bits per second for one node and 129 bits per second for 500 nodes. We can see that the dashed and solid lines for the APCMA curves match very well. For the 6-pulse case, we don't have any simulation results yet. We can also see that the more pulses APCMA uses, the higher the success probability becomes. However, all models shown here for both APCMA and CSMA-CA show rather poor performance when we reach 300 nodes or more. We also get a similar result when we increase the CSMA-CA sleep factor to 10. Since nodes transmit now less frequently, throughput becomes lower, but the relative performance among all considered models remains the same. If we now increase the sleep factor even further to 100, the throughput of all nodes drops to about 8 bits per second, since the ratio of sleeping nodes is significantly increased. Again, all methods behave relatively quite similar with respect to each other, but the number of accommodated nodes is now drastically increased. Our results show that APCMA with 4 pulses reaches about 50% success probability for about 750 nodes, and APCMA with 6 pulses has a success probability of over 85% for about 2,500 nodes. Let us now summarize the results of the previous slides. APCMA shows worse results than CSMA-CA if we use codes with 4 pulses, but the results become better if we use codes with 5 or 6 pulses. APCMA does not require synchronization among the nodes, so the nodes can be very simple devices, having only transmitting units, which reduces the hardware complexity and power consumption. While APCMA packets are longer than those of CSMA-CA due to their unary encoding, this is compensated by their robustness to overlaps in transmissions. Robustness of APCMA increases with packet length, which comes, however, at the expense of throughput. Within our research project, we have implemented APCMA in hardware on Arduino microcontrollers, FPGAs, and the Teensy microcontrollers that are shown here in this picture. In the future, we will verify the results shown in this talk by actual measurements, as well as by an analytical CSMA-CA model. We would like to acknowledge the support provided by the Japanese Ministry of Internal Affairs and Communication in a SCOPE project. Finally, if you are interested in learning more about our APCMA mechanism, please check our other publications listed in the paper's reference section, or contact Ferdinand, Peper, or me by email. With this, I would like to conclude my talk. Thank you for listening.